are the correct measures. I think those who have studied machine learning earlier, they can establish that yes, there are other measures like sensitivity, specificity, recall, and then ROC curve to do the correct evaluation of these models. So basically, we draw a confusion matrix, and then we have this kind of a matrix here where uh, we define the numbers in terms of true positive and true negative, false negative, and false positive. These are very important parameters here to determine the performance of these models. True positive is that your model has predicted that particular example as positive, and it is also positively labeled as positive in the data set. So this should be high. Then we have true negatives. That means the model has also predicted it as negative, and it is also labeled as negative. The other two cases are the false cases, in which it is predicted as negative, however, it is labeled as positive, and the other way, it is labeled as negative but predicted as positive. So ideally, these two figures should be as low as possible, and these two figures should be high. Now, with the help of these four parameters, we can calculate accuracy as, since these two are the correct cases and these two are the incorrect cases, we can have the ratio of true positive plus true negative divided by all the cases. And then we do have another parameters like sensitivity and specificity. In sensitivity, we also call it true positive rate. So it's TP, true positive divided by true positive and false negative, the first row here. In the case of specificity, the second row, it's a ratio of true negative and divided by true negative and false positive. So specificity basically tells you that if the patient is normal, then it's the probability. Specificity is the probability that the model predicts it negative. And in the case of sensitivity, and sensitivity is basically the probability of the patient. If the patient has the disease, then sensitivity gives you the probability that the model predicts it as positive. So it's positive, and model is also predicting it positive. And then we have ROC curve, which you can see ROC curve in which we plot the ratio, plot a graph between the true positive rate and specificity. This is a simple example. Suppose this was the ground truth and test data. The model detects some of them as positive and negative. We can draw this metrics for calculating true positive, true negative, false positive, false negatives. And further, we can calculate the sensitivity and specificity. Further, the ROC curve, we can plot the ROC curve as a ratio between the true positive rate and the false positive rate. And ideally, the area under this curve should be 1. And so basically, we can apply a threshold on the probability being assigned by the model for the output. So for by varying this particular threshold, we can plot the value of true positive rate and false positive rate at certain points and draw this particular graph. So variation in threshold changes the sensitivity and specificity. As a result, we can draw this graph, and we calculate the area under curve. Whichever model has area under curve as 1, that is considered as the best model. Now, coming to some of the data set, the public data sets, which are being extensively used in developing the models. There are a lot of data sets publicly available for development of your models. You can download these data sets, train or develop your models uh, to, and then test the performance of these models. Like if we talk about the MRI based MRI datasets. There are n number of datasets like Open Neuro. This Open Neuro is uh, Open Neuro is for neuroimaging data, and there are total 168 studies, which includes 4,700 patients with various variability in the imaging modality as well as the acquisition protocols. Further, we do have UK Biobank, and in UK Biobank, they have almost 500,000 participants, and it contains MRI images of 15,000 participants, and then it is aiming to reach 1 lakh. TCIA, it is for cancer imaging, and it currently contains 14,355 patients across 77 collections. Abide is specifically for autism brain imaging, and it contains 1,114 datasets from 521 individuals with autism spectrum disorder and 593 controls. Alzheimer dataset, ADNI, and it contains image data from almost 2,000 participants. And BRATS, there are various variants of BRATS, yearly versions. So it's for brain, multimodal brain tumor segmentation. Coming to chest X-ray datasets, there are multiple of them. Like Chexperts, it has large volume of chest radiographs of around 60, more than 65,000 patients, and it's used for competition of different models. Chest X-ray 14, Indian chest X-ray, then other data sets are available for publicly available uh, for developing models for different kind of abnormalities being diagnosed with the help of chest X-ray imaging. Further, histopathology images. I told you that histopathology images is being used for diagnosis of cancer. So one of the popular data set is METOS. It is for mitosis detection in breast histopathology images. We do have another popular public data set, BRACHIS, and it is breast cancer histopathological image classification, and it is comprises of 9,109 microscopic images for breast tumor tissues, which are collected from 82 patients, and it has a variability in terms of magnifying factor. Like the microscopic images are taken on different zoom levels, like magnification factors 40x, 100x, 200x. Rather, it is 400x as well. Further, we do have Chemia Path 24 dataset, and this also contains large number of test batches for histopathology images. Specifically, a dataset is also being developed for detection of ovarian cancer, and it is being collected for 78 patients. This contains the whole slide, stained whole slides, which provides rich clinical information. So these are the data sets which are publicly available for different kind of medical modalities, which can be which are available publicly, which can be used to develop models. You all who have interest in developing your own model for detecting these kind of abnormalities, you can access these data on request from the publisher, and you can develop your own model, test your own model. Now, I think uh, is about that is about the uh, traditional deep learning based applications or use cases in the field of healthcare. We talked about different uh, applications of healthcare. We talked about how we can develop models, what are challenges inherited, what are challenges associated in developing model, what are issues with collection of data set, how we can solve those challenges, in the collection of the data set. We also talked about once we have developed these models, how we can test them, how can we evaluate their performances. So, with that, now it's time to discuss the generative AI perspective of applications in healthcare area. So, firstly, we will talk about some of the basic concepts of generative AI, and then further, we will see how we can use these generative AI based models in the field of healthcare, how we can solve different healthcare challenges using these generative AI models, like the LLMs, like the generative adversarial networks, the diffusion models, how these models can be handy for us to uh, to solve different problems, to solve different challenges which are being faced in the health in the field of healthcare. I just want to tell you that there are certain type of problems which we have seen that they can be solved with the help of traditional deep learning based models. However, with the advent of generative AI based models, we can attempt uh, different problems of healthcare, and we can uh, address the problems which were not being solved with the help of traditional deep learning based models. We will see how we try to how we try to address different concerns of healthcare with the help of generative AI models. Before going ahead, I just want to introduce some basic concepts of generative AI. So, firstly, let's talk about what is generative modeling. So, in generative modeling, the goal is to take uh, various training examples as input from some probabilistic distributions, and then learn a particular model that can represent that distribution. So typically, this kind of setting can be handy. This kind of setting can be helpful in generation of the samples, whether these are generation of the images, whether it is generation of text data, whether it is generation of uh, the audio data. The idea is during the training process, we try to establish the distribution of the input samples, and with once we learn this distribution, we can generate the data which belongs to this particular probabilistic distribution. The whole idea of generative modeling is that how can we learn the p model x which is similar to p data x, which is being derived from the input sample or the training samples, right? So broadly, we can uh, divide the deep learning models into two types. The first one is discriminative models. Another one is generative model. Discriminative models we have seen earlier, like the image classification models, where we provide an input and these discriminative models are responsible for classification of that input data. They basically extract meaningful information from the data to discriminate among different classes. However, in the case of generative models, these generative models can generate new data instances based on the learned probability distribution of the existing or the training data. In this example here, you can see a small a part subpart of a sentence or a paragraph is given as an input, and this text generation model or any generative model can generate the complete paragraph given a subpart of that paragraph. So that's the basic difference between the discriminative and the generative models. Sorry. So that's another example, the visual depiction of discriminative and generative models. You can see here these discriminative models, they are used to classify or predict the labels from the data points. They are typically trained or on a label data set. I told you the supervised machine learning type of models, where we provide the data uh, along with the label to the model during the training process. Basically, the idea of discriminative models is to learn some kind of relationship between the input data or the features of the input data and the corresponding label. So the discriminative models basically learns a function, a mapping function uh, between the input data, which could be image, audio, or text, and the mapping function from between this input data and the corresponding label. However, in the case of generative models, these generative models basically generate the data which follows the same distribution as of the training data. In this example, a dog image is being generated based on a given input dog image. However, in this case of discriminative technique, we are assigning a label to the given image. So, simple uh, depiction: predictive or discriminative model learns the relationship between the data and the label. Given data, given label during the training process, the model is trained. It's a predictive ML model, and then it gives you the output and as a label of that data. However, in the case of generative AI model, this learns the pattern of generative new content to generate a new content. It learns the distribution of the input data to generate the new content. Basically, let's define what is generative AI. The generative AI, mainly it's a branch of artificial intelligence, of course the subset of deep learning. So the generative AI is the advanced form of deep neural network which we studied earlier. The modern generative AI models like transformers or the LLMs, they have deep neural networks, the advanced form of deep neural network. And the main focus of generative AI model is to generate new content. And the outcome is that the generated content resembles the existing data. Another point to note here is they process large volume of data. They are data hungry models and they need large volume of data for training. And they process large data and detect some kind of pattern from the large data being provided, and then they are capable of creating new works like text, imagery, video, or even they can create software programs, computer codes based on the instructions that are given to these models. We call these instructions as prompts. Remember the first slide which we talked about? I gave a prompt that I have 101 fever and symptoms of cold, and based on that prompt the generative AI model gave generated suggestions based on that prompt. Now these generative models, they can process both labeled as well as unlabeled data. They can be supervised or unsupervised or maybe semi supervised kind of methods. Some of the examples of generative AI models are like LLMs, generative adversarial networks, variational autoencoders, the diffusion models. Some of them we will be studying in this particular talk, and we will be seeing how these generative AI models are effective in solving different healthcare problems. Now, coming to the types of these generative AI models, the first one, text to text. You have already seen the example where I gave a text prompt and I got a result as a solution in text. So they basically takes natural language input. We say the text inputs as natural language inputs, and they produce the text output. Some of the examples in medical domain could be translating the patient education material from one language to another language. Let's say some patient education material is being developed in English language, and with the help of these text to text type of generative AI models, we can convert that educational manual into Hindi or any other language. Or maybe with the help of these text to text generative AI model, we can summarize a medical domain research paper into a plain language. We can generate a summary of research paper. Further, we have text to image type of generative AI models. They are they are basically trained on large set of images, and for each image, let's say we have captions or a short description. So basically, one of the example I can present here for this type of generative AI model is generating or editing an image which corresponds to a specific medical condition or a procedure. Let's say I ask the generative AI model that create an X-ray image which has symptoms of tuberculosis. So that type of application comes under this category of text to image generative AI model. Further, further we have text to video or text to 3D type of model. Uh, like for example, we can ask the generative AI model that generate a video in which a patient is being demonstrated how the patient can do certain exercises at home. So, given a text prompt, the generative AI model has to develop or generate a video based on whatever instructions are given in that prompt. So that's the third type of that's the third type of generative AI model. We can have combinations of these types of models. Maybe we can say that give a prompt as generate a similar video which is attached with this prompt. So in that case, we have text as well as video as a prompt, and then a video is being generated by the generative AI model. Now, this term you must have heard multiple times, like foundation models. And when the news came for DeepSeek, there was a lot of buzz that China has developed their own foundation model. So, what exactly this foundation model is? Let me explain that. So, these foundation models are basically they are trained on a broad data, generally by using self supervision at a scale. And then the idea is we can say that these foundation models are generic in nature. Once these foundational models are developed on vast data, they can be further adapted to specific kind of tasks. Like you can see in this diagram here, the foundation model is trained on variety of data like text, images, speech, structured data, or 3D signals. Now, once this foundation model is developed, we can adapt this foundation model to perform various tasks like question answering, sentiment analysis, information extraction, captioning of the images, recognition of the objects, or maybe following certain instructions, and so on. So that's the idea of foundational models. I can tell you some of the examples like BERT, GPT-3, CLEP. These are some of the popular foundational models. Now, how we can use these Yeah, welcome back. I hope I am audible now. There was certain issue related to the internet here, and I'm sure I'm audible now. All right. Please confirm if I am audible now. Yes. Okay, fine. Let's continue. Okay. Before we continue, I just want to answer the queries which were asked in the chat box. Uh, there was one query related to if multiple filters are applied on image in same convolution layer, then why they do not converge to same value to minimize loss. I didn't got the question. I think uh, the weights are different for different filters, and they are responsible for extracting different information from the image. So that's why the value of the weights is different. Their task is different. So whenever we are training the model, that means we are learning these weights of different filters, and but I mean, different filter weights are being learned simultaneously. Another one is, sir, generative AI medical images from text. How can we ensure they are clinically reliable and ethically safe for healthcare decisions? So this is a topic of discussion. Uh, Uh, there are always ethical issues, but nowadays I think we have started seeing lot of AI based medical devices. So there is a particular certification process or licensing processes for these kind of equipments or devices, and also I mean, uh, these licensing agencies are there in each of the country. FDA is in US, or we have CDSCO in India. So they, uh, I mean, they do consider these AI based software as one of the medical device, and while giving licenses to these devices, a thorough testing has been is being done, and then only they are given licenses so that they can be used to take healthcare decisions. So I mean, there is complete licensing mechanism, testing mechanism, to ensure that whether they are clinically reliable or not, whether they are ethically safe or not, then only they are being inducted to take healthcare decisions. I hope the answer is clear. Fine. Let me share the screen again and continue where we left. I think I was not audible for last 2 3 minutes, so I'll come back to that slide again, and then we will continue the discussion. So I hope I was there on this particular slide. I'll start the slide from the beginning. Now, in this particular slide, we are going to discuss about the use cases of generative AI in the healthcare. There is lot of use cases which are being summarized in this particular slide. So I'll like to devote some more time on this particular slide. We will talk everything in detail. So what I can say here is, these are different models which are generative AI based models, and which are being extensively used for generation of medical related data. And these are capable of, I mean, these generative AI based models are capable of generating realistic and anonymous patient data. And once these data are being generated, they can be helpful or handy for research and training purposes. Also, they enable a wide range of versatile applications which are shown here. As I was telling you, the major problem from AI perspective in the healthcare field is related to the data. We have scarcity of data, and it is very cumbersome to collect new data, or there is limitation in developing the data sets. We ourselves are working on multiple projects where we are collaborating with different doctors, and it is, frankly speaking, it is very challenging to collect data from different hospital. There are certain ethical issues which we have to address, and there are a lot of challenges, specifically when we talk about the collection of the data sets. So these kind of tools, like generative AI based tools, where we can generate synthetic data with certain kind of abnormality, these could be very handy. So uh, I mean, data generation, there could be text generation. So text generation, what could be the use of text generation in medical field? The reports, the diagnosis reports, the summary of the patients, they are in text format. So given an image, generation of the summary or the diagnosis report based on the image, that can be uh, generated with the help of these models. Generation of images, so we can give a prompt like generate an x-ray image with abnormalities such as TB. That could be helpful for training or the research purposes. We can generate other kind of data, like uh, unique uh, chemical structures. We can generate novel or small molecules, nucleic acid sequences, or proteins with desired properties or desired functions or structure, and thus it can help us in drug discovery. Further, I mean, these generative models, they can be trained on vast or a large volume of data sets of medical records, or the corresponding imagery like the MRI, X-ray, or the CT scans. And uh, I mean, these models can identify different patterns related to different kind of diseases. For example, the particular generative AI model called as generative adversarial network (GANs), they have been extensively used for image reconstruction, low quality handling or processing the low quality images, or synthesis or segmentation or classification of the images. Further, like the models like LLMs such as GPT-4, GPT-3, and Palm 2. Palm 2 is one of the model proposed by Google, and they are very handy in generating summaries of patient data. Let's say a patient has a historical data of last 2 3 years or maybe more than that. It has a very large big file with them, and suppose the patient goes to a new doctor. The doctor will need at least uh, 1 or 2 days to study that whole file. Why can't we have a generative AI model which can present a summary of the whole large file in 2 pages? It will be helpful for the doctor to quickly take decision for that particular patient. So the models like LLMs or Palm 2, they can be used to generate the summaries based on the patient data available. And I mean, this kind of solutions can be handy. These kind of solutions can be helpful where we have large volume of data, and we have heavy burden on the healthcare practitioners. We have electronic health records. I mean, nowadays every hospital has implemented electronic health report which contains the medical data, or the medical data of the patient, like medical history, or what kind of medication was given in the past, or I mean, what kind of allergy that patient have, and uh, the diagnostic or the laboratory results. So these electronic health records can be used as an input to these generative AI models. These generative AI models can be trained on these electronic health records, they can read through these datas, they can understand the important points, and then generate a concise summary for the doctor to take important decisions related to the diagnosis of the patient. And further, I mean, we talked about synthetic data, we talked about medical diagnosis, then clinical documentation. Yes, with the help of these models, we can generate clinical documentations like patient manual. We can generate certain personalized manuals for exercising or other kind of implementations. We can generate uh, manuals for medical education and training. I mean, we can generate education contents and how to handle a particular specific patient condition or specific patient symptoms or questions. Suppose a patient has diabetes, and then AI, the generative AI models can generate a booklet about how to manage the blood sugar level, what to do when the sugar level are low, what to do when the sugar level is high. uh, the booklet can contain the diet chart, they can contain the exercise or medication schedule. So all these can be generated with the help of these models. So this was about, I mean, also, yes, based on uh, based on the medical history, based on the allergies, based on the diagnostic results, these models can help in finalizing the personalized medicines. Another typical use case of these models is healthcare administration. There is a lot of tasks which are involved in management of any of the hospital, like we can have chatbots at the entry of the hospital where initial information can be captured and initial questions can be answered. These chatbots can be installed on the mobile phones of the patients. They can help in scheduling the appointments. I mean, these chatbots can suggest suitable time for medication. These chatbots can suggest suitable time for appointments. Uh, there are bed management, availability of beds in the hospital. All these managements, healthcare hospital administration can be managed through these type of generative AI models, and we have started seeing use cases live in the hospital these days. uh, uh, these hospitals are evolving in a faster manner. Everybody is implementing, I mean, everybody is keen to implement these generative AI use cases in their hospitals. Fine. Now, coming to the modalities which these generative AI based models can process, these are, I'm sorry, like natural language based modalities, natural language based data, the discharge summary, the diagnosis report, the patient history, and all. Then we have image based modalities. We talked about MRI, we talked about histopathology images, we talked about uh, the CT images or X-ray images. Then further, we can have audio images. Like one of the project we are working on, digital stethoscope, in which we are recording the heart audio using the stethoscope. So audio can also be a modality for as an input to these models. These models can work. Uh, I mean, they can use these data for different applications. We'll talk about some more generative AI use cases in the real life. Earlier slide basically talked about where we can use these generative AIs. In this particular slide, I'll talk more about the actual implementation of these models, they are being used in real life. One of the typical example is from Google, where they have developed a MAD Palm, a large language model developed by Google Research, and this is specific model uh, which is being developed for medical domain. Now, another example is Meta's open large language model, which is optimized or downloadable as a NVIDIA NIM, and this basically powers the digital health and life sciences workflows. Further, we have Google's medical AI chatbot, which is already being tested in multiple hospitals. Mayo Clinic is one of such hospital where Google's medical AI chatbot is being continuously under testing. From Microsoft, Epic and Microsoft brings GPT-4 to electronic health records. So they have integrated the generative AI models to the electronic health records, and with that, uh, the healthcare practitioners can improve the productivity and communication with the patients with these kind of solutions. Now, coming to the basics, let's talk about some of the basics, how these generative AI models can help us in solving these healthcare tasks. What are these complex terms like large language model, and how do they work? So let's have a quick overview of these working of these models. Like, firstly, what exactly are large language model? The name itself tells you they are large models. They are related to language, and of course, they are generative AI models. So these are large general purpose language models, and they are basically pre-trained, as I was telling you, the foundational models, and then further these LLMs can be fine-tuned for specific purpose. Like I gave you an example of automatic question answering or generating the summaries and so on. Further, uh, as we were discussing earlier, these large LLMs are trained to solve common language problems like text classification, question answering, summarization, generation, and then these models can be tailored to solve specific problems. And why the term large? Because they are trained on large data set, firstly. Secondly, they have large number of parameters. What does these parameters mean? Recall our discussion on deep learning, where we were calculating those number of weights and biases. So those were the parameters of any neural network which need to be trained. So basically, these large language models have billions of parameters. So while training these models, we need large volume of data, and then we need to train these large number of parameters. So basically, we need a large compute power as well to train these models. So basically, how do they work? And as you must have seen, large language models has been extensively used for generating or predicting the next word. So in this particular example, the vector representation, suppose I'm inputting sub part of a sentence like the cat sat on, and this model has to predict the next word which should come after on. So what do? We basically convert these words uh, into input tokens. So basically, these are the vector representation of these tokens. They are being passed through these LLMs. So we can say that these tokens are basically the atomic unit of on which the LLM works. They are being passed through this LLM, and then the LLM basically gives you the vector representation of the next output token, or you can say the next word. And The whichever word has the highest probability, that will be the most likely next word, and so that will be chosen as the next word of this in this sentence. Coming to how these LLMs can be used in healthcare, uh, firstly, we can talk about these EHRs we have reports. We can have different type of healthcare data, millions of EHRs. Then we can have a medical foundational model. So basically, with large volume of healthcare data of wide variety, we can train a medical foundational model. Then further, this medical foundational model can be adapted to a specific question, a specific task, and this LLM can be integrated with a chatbot where we have natural language interaction, and given a particular prompt or instruction, this adapted medical foundational model will be answering the chatbot related to different tasks. So this is another depiction of it. We can have large volume of data like research papers, clinical notes, or medical textbooks or reference material, healthcare reports, patient education material. With that, we can have a foundational model, and then further we can adapt it for tasks like translation from one language to another language, or question answering related to healthcare, or text summarization, text generation, and so on. One of the example I gave you earlier as well. Let's see another example, like a prompt is being given to open gpt: what is vitamin D3 used for, and should I take it or not? Now you can see here the NHS LLM, which is a medical LLM being trained for medical domain. It gives you an answer that vitamin D helps regulate the amount of calcium and phosphate in the body, and which is necessary for keeping bones, teeth, and muscles healthy. Most people should be able to get all vitamin D they need through sunlight on their skin and for a healthy diet. It has also given uh, a reference to it from where it has taken the description. So, question answering, LLMs can be very handy in answering certain uh, in answering questions related to medical domain. Another use case of LLM is, suppose a surgery is being done, and an operation note is to be generated or prepared by the surgeon. So, given a prompt like generate an operation note, and what was the abnormality? It is repair of Leclerc to the dorsum of left hand and repair of superficial branch of radial nerve. This was the text prompt provided to the medical LLM, and then it provides you the operation note. It generates the operation note. It gives you the format of the operation note, and some of the fields are already being filled based on the training data which was provided to it. So this could be helpful in automatic generation of medical documents, and the information, further information can be easily filled by the doctor. So it will be handy, helpful, rather than writing a long operation note by hand. This generative AI based model or the tool can generate that operation note, and that can be used directly by the surgeon or the doctor. Now, there are certain general purpose or specialized medical LLMs. Like these are the general purpose: BioGPT, Clinical BERT, PubMed BERT, and there are certain medical LM, Biomed LM, SciBERT, Image BERT, and so on. These are uh, the LLMs for medical purpose. We already talked about different. I mean, These LLMs can be of multimodal type. That means they can handle, not only they can handle the text data, they can handle multimodal type of data. Like coming to the text data, it can handle clinical notes, research papers, patient instructions, medical coding terminology. Coming to image data, we have already talked about different type of medical data, even covering the microscopic pathology slides. Structured data like the signals, ECG, EEG signals, or the demographic data, or the lab results. And videos, remember we talked about the types of models like text to video, so they can handle the videos as well, surgical recordings, gait analysis of the patients, 3D medical models, or exercising videos, or other medical domain videos. So with that, I would like to have a small break of 5 minutes. It's almost 7 now. Let's meet at 7:05. Let's have a quick bio break, and then we will continue our discussion for another 1 hour on application of generative AI. We will take some typical use cases, how we can use these generative AI models, specifically diffusion model, generative adversarial network models, for solving different healthcare related tasks. In the last, we will discuss certain projects which we are working in the healthcare domain. Let's meet at 7:05. Welcome back to the third session of today. Let me continue where we left. Uh, Fine. So we were discussing the multimodal medical LLM, which is capable of handling multiple type of data. Now, coming to the main building block of these uh, large language models, and at the core it is transformer which is uh, enabling these large language models. Transformer is basically based on the 2017 paper, and the name of the paper was "Attention is All You Need." And basically this 2017 was the eureka moment for natural language processing. In the similar fashion, the 2012 was the eureka moment for computer vision domain. There were a lot of models before transformer, and which were able to represent the words as vectors, and these vectors basically they didn't con- contain the context, and the usage of the word changes based on the context. That was the problem with the earlier models, the sequence models, like RNN and LSTMs. For example, like suppose bank and river bank versus bank in bank. Uh, Rover might have the same vector representation before attention mechanism came about. So that's the basic difference between the models prior to transformer and then uh, with transformer based models. So coming to the transformer, what exactly is transformer? This is the paper which I was referring to, and transformer is nothing but it's a encoder decoder model, and that uses the attention mechanism. It is better than RNN LSTM, and it takes advantage of the parallelization of GPU and TPU, and it can process much more data in parallel in the same amount of time. And I mean, the architecture of transformer is in such a way that it can process all the tokens. I was telling you, token is basically one computing one unit on which it performs. So it can process all tokens at a same time. These the transformers are basically they are built using the attention mechanism at the core, and it consists of encoder and decoder model, which is being shown here. The encoding component, it has multiple stack of, I mean, it has a stack of encoders, and um, the 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 research paper in which the transformer was proposed, it the stack consists of six encoder on top of each other, and six is basically the hyperparameter which we can change. Now let's break down this particular encoder, and it can be broken into two sub layers. One is the self attention layer, and another one is the feed forward layer. So feed forward layer you have already gone through in our previous lecture. However, let's talk about what is this self attention. So in this self attention, the input of the encoder are first, they are being flown through the self attention layer, and actually the uh, idea of self attention is to encode or to search or look into the relevant part of the words, uh, as it encodes the central word in the input sequence. That means, let's say we have a larger sentence, we take I mean, all those tokens are processed in parallel, and whichever word is highlighted, I mean, we compute the attention corresponding to that central word in the self attention layer. And then it is being passed through the feed forward layer. And similarly, in the decoder also has self attention as well as the feed forward layer, but between them it also have encoder decoder attention layer, which you can see here. This is encoder decoder attention layer, which is different from the encoder part. And this basically helps the decoder. What is the use of this encoder decoder attention layer is, it helps the decoder to focus specifically on the relevant part of the input sentence, which uh, word should be given more emphasis. That is being helped by this particular encoder decoder attention. Now, this is a typical example of how transformer works. Suppose this is language translation from one language to another one, and I was telling you all the tokens are processed in parallel. So, in the encoder part, firstly we have self attention, feed forward, and this basically allows us the parallelization. So, firstly, this is converted into vector representation. It and The embeddings of these words are calculated, and they are flown through these two layers of the encoder, and the uh, word at each position passes through this self attention. So basically this self attention vector is calculated for each of them, keeping the particular word or the token as the central word, and then it passes through the feed forward neural network, and further it is being applied. So there is a stack of encoder, they are being repetitively being used as stacks. So this is another example, clear depiction of transformer, how the self attention works, in which we have query, key, and value vector. They have their own importance. I'm not going into much detail of these technical aspects of transformer. You can have further uh, you can learn further related to transformer from other relevant sources. Let me go through how these models are being used for solving different medical solutions. So we'll take some of the case studies here, and we'll see how we can use these large language models to solve different tasks of healthcare domain. Firstly, one of the popular uh, language model specifically for solving vision related tasks is vision language model, VLM, which is one type of large model. And this particular vision language model can be handy in processing multimodal data consisting of visual as well as language data. And then you can see the flow chart here, what all tasks we can solve with this vision language model. It can take visual modalities like x-rays, histopathology images, CT images, and MRI images, and it can take language modalities like medical report, other relevant language data, and then this language modalities can be passed through the encoder, which is responsible for handling the text data, and these image related modalities, visual data, can be passed through image encoder, which is responsible for only image data. And the structure of the encoder we have already discussed when we were discussing about the transformer. And then these two outputs of image encoder and text encoder are provided to the vision language model, which is responsible, or which is capable of handling both vision as well as language data, and they are being fused. And further, there are different downstream tasks can be performed using the data which is being generated from here. For example, the vision related task, segmentation of the image modalities, classification of these image data, detection from these image data. Coming to the natural language outputs, we can generate a report for a given visual modality. We can have question answers, or maybe we can generate new image based on the text prompt. So this particular paper proposed the application of this vision language model in the medical image analysis domain. It says that vision language model in medical image analysis, from simple fusion to general large models, and this was published in information fusion. Now, coming to another type of generative model, which is generative adversarial network. And the idea of generative adversarial model network is to have two separate parts, like generator and discriminator. The generator generates fake samples and tries to fool the discriminator. The discriminator tries to discriminate or distinguish between the real and fake. As a training part, we train them against each other. That means the generator is being trained to generate fake samples which looks like real, and the discriminator is being trained to discriminate between real and fake samples, and then repeat this training process till the time we get better generator and discriminator. Let me show you the architecture of generative adversarial network. You can see here, this is the generator Z and this is the discriminator D. This generator samples the data from latent random variable, tries to generate a sample which follows the distribution. Further, we do have a collection of real world images. We sample one data from this one. Both of them goes to the discriminator module, and the discriminator module basically tells us whether it is real or fake. And further, we compute the loss, and this loss is being used to train these discriminator and generator simultaneously. So, in this race of generating fake samples by the generator and discriminating the real and fake samples by the discriminator, the generator becomes so efficient that it it is able to generate images which looks like real one. So that's the whole idea of this generative adversarial networks, and they are capable of generating synthetic data which looks like the real one. Let us see some of the results of generative adversarial network for medical image analysis. This paper of 2022, the role of generative adversarial network in medical image analysis, which presented the application of GANs in medical image analysis. You can see here there are multiple applications of GANs, like cross modality data generation, segmentation of the data, reconstruction of the data, augmentation of the data, or detection of the data. So basically, the problem in, as I told you earlier, the problem in medical data sets is that they contain more negative data than positive samples. And the drawback of the supervised kind of learning model is that they require enormous amount of data to train, and they, they have to generalize on the new data. The supervised learning models need labeled data of different classes. So basically, GAN helps us in synthesizing these data set images, and then we can transform them from one class to another in a realistic way. So that's the power of generative adversarial networks whenever we talk about generating synthetic images. This is one of the example where the GAN is being used for medical image augmentation, and this was specifically used for generating uh, COVID-19 based chest X-rays. The name of this particular model is COVID GAN. You can see here we have a generator model and another one is discriminator model. This generator model basically takes input uh, and generates fake image, and uh, the real data, the ground truth data, is also being provided to the discriminator. This discriminator tries to discriminate between the fake data being generated by the generator and the real data sampled from the data set, and it tells you real and fake. And this is being trained in such a way that this generator basically generates the images which looks like the real ones. Some of the examples are here, which are taken from one of the paper in Nature. These are the images being augmented or generated with the help of generative adversarial network. Now, coming to the third type of generative model is diffusion model, and the idea of I'm sorry. The idea of this diffusion model is to systematically or slowly destroy the structure of the data through an iterative diffusion process, and then try to learn reverse diffusion process that restores the structure of the data, and which results in yielding a high quality data as a resultant. So let me pose it in other words. We can add noise to an image iteratively in iterations, and then what we can do is we can train a model that learns how to denoise this noisy image, and thus in this process of denoising the image, it can generate novel images. So the goal here is we want to have a model which learns to denoise or to remove the noise, thus generating new images. So firstly, what we can do, uh, we can start with a forward diffusion in which we can go from x0 and the initial image to x1 and the initial stage with a little bit of noise added to it. We can do this again and again. You can see here noise forward diffusion. Again, as a result, it becomes a pure noise. And during the reverse diffusion process, this pure noise is denoised using this diffusion model to generate a clear image. So this whole process of generating the noisy image and then further developing a model of reverse diffusion where from this noise we generate a new image. So that model is for generating novel images. So that is how it works. The original image process of adding noise, slowly iteratively we add noise to this image to bring it to a pure noise image, and then further in the reverse step we apply step by step denoising process that transform this pure noise into the data sample. So basically the neural network here is being trained to predict the noise. So that's a reverse diffusion process. So how do we do this? We add the noise to it, get the noisy image. Finally, we apply a denoising model, predict the noise, calculate the loss, and update the parameters. Slowly, this denoising model will be updated in such a way that it can generate a novel image given a pure noisy image. So there are certain use cases of diffusion models like unconditioned generation of data, maybe synthesis of human faces, super resolution of the images, or maybe conditioned generation. Generation means giving a prompt, and with that we can generate new data like text to image. One of the example given here, Mona Lisa with cat face, and then image impacting, removing the woman from a particular image or removing a particular object from the image, or maybe text guided image to image like disco dancer with colorful lights. That's quite funny. uh, this is typical example of diffusion model, and being this diffusion model is being used for generation of realistic chest x-ray images with a given prompt, a text prompt like this particular abnormality given as a text prompt input. uh, we This model has to develop or generate a chest x-ray image with these kind of abnormalities or these kind of features. So to start with, this text prompt is given to the text encoder, and this random Gaussian noise is being given. Since we have studied that diffusion model takes the pure noisy image as an input, and then this model learns a denoising model to get a novel image here. So here in this particular example, they have used a variational autoencoder as well for generation of the chest X-ray image. These are some of the examples here, like the diffusion model-based generation of realistic chest X-ray images. These are with different kind of abnormalities. This paper was Roent Jen Vision Language Model, foundational model for chest X-ray generation. So these are different kind of abnormalities which are there in the chest X-ray images. Another one of the example of generative AI, specifically generation of images, DALI, and this DALI based image generation is being shown here. They are able to generate hyper realistic AI generated images, specifically for different kind of skin abnormalities. So this was about the application of generative AI in the healthcare. Now, I would like to quickly discuss what projects we are doing in our research group. The first project is related to AI-based urine sediment analysis. This is one of the proof of concept which we have developed. Uh, uh, most of them, most of us must have gone to diagnostic labs for urine tests. So one of the urine test in the normal urine test is microscopy based test, in which the doctor, the pathologist, see the urine slides on the microscope and then counts the number of sediments like WBC, RBC, and other sediments and do the reporting. We have automated this particular task, this particular uh, manual task, in which we have put a camera over the microscope, and this camera can capture this camera is attached with a computing board, the embedded board, and this camera can capture high resolution microscopic slide images, and then further these microscopic images can be fed to AI models, which the custom AI models which we have developed, and these are the results which are being uh, given by our model. And I just want to clarify here that these results are, I mean, the performance of these models are really good. We have developed this model uh, developed this model using deep neural network, and we have collected our own data set which comprises of more than 5,000 images, microscopic images of different urine samples. We collected leftover urine samples from different hospitals and collected our own data set and developed the custom deep learning model. You can see the results here. It is not only detecting, these dots are basically detections, not only detecting, it is counting and presenting the comprehensive report of this microscopic urine analysis. These are RBCs, these are some of the crystals. Another project which we have developed, for which recently we are granted a patent, an Indian patent. This particular device, this is a portable AI device which is capable of detection of silicosis from chest X-ray images. Silicosis is one of the life-threatening disease which is prominent in mining workers due to inhalation of different dust particles. So the idea of this particular device is to make it a screening device. This is capable of interfacing with any digital X-ray machine, or we can provide the digital X-rays in pen drives. This particular device can read the X-ray, digital X-ray. AI model is being developed, hosted on the embedded computing hardware, and further it can give uh, analysis of that chest X-ray, whether silicosis is there or not, and if yes, what all are the reasons of the chest due to which the model has predicted silicosis. Those reasons are being highlighted with the severity. So these are some of the typical use cases which we have developed in our lab, and a few of them are under consideration for commercialization through one of our startup. And I think let's conclude here. I would like the participants to raise the questions. Uh, the floor
So for
is
the question,
open for
here, yes,
question
question.
answers.
If at all any there, Sadanan, please read it out because I am not able to see. If at
Yes,
all any question.
I have already opened the chat
Okay,
box. So
okay,
all
okay, okay. Thank
participants
you,
are
sir.
requested to please write their questions on in the chat box. We have enough time. We can take multiple queries. So any query related to previous lectures or any queries related to today's lecture, please feel free to ask them.
Request
Be
you to
happy to
read.
answer those queries.
No question. Okay, then
Yes.
thank you, sir, for
And thank you, sir,
thank you
for
for
giving me the
joining.
opportunity to share the research with the participants.
Okay, okay, okay. Thank you, thank you. So, participants, with that, we are ending of our today's, that is day 7 of our online FDP. See you tomorrow at 5 o'clock. Okay, thank you, all of you.